Hello, higher physicists. Today we're going to have a look at the electricity questions from the higher physics paper in 2018. So without any further ado, the first question is question 11, and it says, a student constructs a battery using a potato, a strip of copper, and a strip of magnesium. And we can see that in the diagram here. The student then sets up the following circuit with the potato battery connected to a variable resistor R in order that the electromotive force, EMF, and internal resistance R of the battery may be measured. So we can see here they've set up the potato battery, which effectively is made up of a battery and an internal resistance, connected in series with an ammeter and a variable resistor, and a voltmeter connected across the potato in order to measure its terminal potential difference. And the first part of the question asks, what is meant by the term electromotive force, EMF? So this is a standard definition, one that we just need to understand and know that the EMF is the energy gained by each coulomb of charge passing through the cell or battery. Part B says the student uses readings of current I and terminal potential difference V from this circuit to produce the graph shown. We can see this downward sloping straight line. Determine the internal resistance of the potato battery. So we have this graph. How can we use that to work out the terminal potential, the internal resistance rather? Well, we have this formula for EMF and internal resistance, E equals V plus IR, where E is the EMF, V is the terminal potential difference, I is the current, and little r is the internal resistance. Now, if we rearrange that a little bit, we can get this. V equals minus Ri plus E. Now, your maths teacher is bound to have explained to you that for any graph with a straight line, the equation for that graph is of this form, y equals mx plus c, which means any point on the line, the value of its y value is equal to the gradient multiplied by the x value plus some constant, which is the y-intercept. Now, if we compare that formula, y equals mx plus c, with the one above it, v equals minus ri plus e, you'll see they're very similar. And if we look at our graph, we'll see we have v on the y-axis, we have I on the x-axis, and therefore we can match up these letters, and the internal resistance, or the negative internal resistance, is equal to the gradient of the line. So we can find the internal resistance by working out the gradient. So we need to pick a couple of points on the line that cut through the corner of a box that are nice and easy to judge, and then work out the gradient, y2 minus y1 over x2 minus x1. And I looked at that and found 2 points where the line cuts through the very corner of a grid square, and I got y2 to be 380 milliamps, or 380 millivolts, or 0.38 volts, minus y1, 670 millivolts, or 0.67 volts, divided by x2, which is 80 microamps, minus 0. And that gives me a gradient of minus 3,625. That gradient is the negative internal resistance. So the actual internal resistance to two significant figures is 3,600 ohms. The student connects a red LED and blue LED in turn to the battery. The LEDs are forward biased when connected. The student observes that the battery will operate the red LED, but not the blue LED. The diagram represents the band structure of the blue LED. LEDs emit light when electrons fall from the conduction band into the valence band of the p-type semiconductor. So, what needs to happen? Well, the difference between a red LED and a blue LED is the light that they emit. The red LED emits light of a longer wavelength or lower frequency or less energy than a blue LED. That means that the band gap for a blue LED is larger than for a red LED and therefore requires more energy to push electrons through from the conduction band in the N-type material and into the depletion layer and drop down into the valence band of the P-type material. So, explain using band theory why the blue LED will not operate with this battery. I wrote that the electrons in the conduction band of the N-type material do not have enough energy to overcome the depletion layer and move towards the P-type material. However, they would in the red LED because the red LED requires less energy because the band gap is smaller. Number 12, more about LEDs. A student carries out a series of experiments to investigate alternating current. A signal generator is connected to an oscilloscope and a circuit as shown. And we can see here the signal generator connected to the oscilloscope and also to the circuit, which contains a red LED and a blue LED. The signal generator is a device which basically produces an alternating current. The output of the signal generator, that alternating current, is displayed on the oscilloscope. The Y gain setting on the oscilloscope is 1 volt per division. The time-based setting on the oscilloscope is 0.5 seconds per division. So the oscilloscope basically draws a graph of voltage against time. So the vertical axis is telling us about voltage, and the horizontal axis is telling us about time. So part 1 asks us to determine the peak voltage of the output of the signal generator. So looking at the graph, the peak voltage is obtained by working out how far from the zero line the curve goes, basically the amplitude of this signal. And as it says here, the Y gain setting on the oscilloscope is 1 volt per division. So the peak voltage is 3 boxes at 1 volt per box, which gives us a total of 3 volts. Part 2, determine the frequency of the output of the signal generator. Well, the frequency is given by, or is obtained from the period. The period is the time for one complete cycle. And we can see here that one complete cycle is 4 boxes. And 4 boxes are 0.5 seconds per box, which is a total of 2 seconds. The period can then be used to work out the frequency. Frequency is 1 over the period. So 1 over 2 seconds, which is 0.5 hertz. Part 3. The student observes that the red LED is only lit when the ammeter gives a positive reading, and the green LED is only lit when the ammeter gives a negative reading. Explain those observations. So if we have a look at the circuit here, we'll see that the 2 LEDs are connected the opposite way round. The red LED is sort of pointed towards the left of the screen, and the green LED is pointing to the right. Now we need to remember that LEDs, or diodes in general, are directional devices, which means they only allow current to flow through in one direction. So since the 2 LEDs are connected the opposite way round, one will allow current to flow when it's flowing in one direction, and one will allow current to flow when traveling in the opposite direction. So as the LEDs will only conduct when forward biased, when the current changes direction in this alternating current, the bias of the 2 LEDs swap over. So one would light when the current is passing one way, and the other would light when the current reverses and is passing the other way. B. The signal generator is now connected in the circuit as shown. The settings on the signal generator are unchanged. The signal generator has negligible internal resistance. Determine the RMS voltage across the 82 ohm resistor. So let's have a look at the circuit. We found out way back at the beginning of the question that the peak voltage being given from the signal generator was 3 volts. That is our supply voltage. We have two resistors, R1 and R2, and in any series circuit, the supply voltage will split between the components within the series circuit, a potential divider effectively, and give us a value of V1 and V2. And if we want to work out one of those voltage values, then we can use this formula. V2 equals R2 over R1 plus R2 times Vs. We insert our numbers into the formula and get a value for V2 of 1.64 volts. That is the peak voltage across V2 because we use the peak voltage for the supply voltage. If we want to work out the RMS voltage, we need to use RMS is V peak over root 2, which is 1.64 divided by the square root of 2, which gives us 1.2 volts. And that takes us to the end of the electricity questions from the 2018 higher paper. I hope this was helpful for you, and I will talk to you again sometime soon.